Chapter 14, Section 2, Properties of Fluids. And before we start, remember that the numbers over here, like this 34, correspond to questions on your reading guide. So the main idea for this section is fluids flow and exert forces on objects. So the real-world reading link, have you ever seen an aircraft carrier? Although these ships are composed of metal and sometimes weigh more than 100,000 tons, they still float. So how is this possible? Archimedes Principle and Buoyancy. Some ships are like floating cities. For example, aircraft carriers are large enough to allow airplanes to take off and land on their decks. Despite their weights, these ships float. There is a force pushing up on the ship that opposes the gravitational force pulling the ship down. What is the force pushing up on the ship? It is called the buoyant force. And the buoyant force, if it's equal to the object's weight, then the object will float. If the buoyant force is less than the object's weight, the object will sink. So buoyancy is the ability of a fluid, which is a liquid or a gas, to exert an upward force on an object immersed in it. That's our definition for buoyancy. Now, Archimedes Principle. In the 3rd century BC, a Greek mathematician named Archimedes made a discovery about buoyancy. Archimedes found that the buoyant force on an object is equal to the weight of the fluid displaced by the object. So, for example, if you place a block of wood in water, it will push water out of the way as it begins to sink, but only until the weight of the water displaced equals the block's weight. So when the weight of the water displaced, the buoyant force, becomes equal to the weight of the block, it floats. If the weight of the water displaced is less than that of the block, then the object sinks. And figure 13 shows the forces that affect objects and fluids. So, for example, our block of wood over here. So we have a block of wood, we put that in the water, it displaces water until the amount of water displaced weighs the same as the block of wood. The block of wood So in the case for the block of wood, the amount of water displaced equals the weight of the block, so it floats. In the case of our block of steel over here, the weight of the water displaced does not equal the weight of the steel. So we have this smaller arrow here. So our buoyant force is smaller than the weight of the block. For the case of the wood over here, the buoyant force is actually equal to the weight of the block, so it floats. Comparing buoyancy and weight. Look again at the wood and steel blocks in figure 13. They both displace the same volume and weight of water when submerged. Therefore, the buoyant forces on the blocks are equal. Yet the steel block sinks and the wood block floats. What is the difference? The steel block weighs more, or weighs much more than the wood block. The gravitational force on the steel block is enough to make the steel block sink. The gravitational force on the wood block is not enough to make the wood block sink. Density and buoyancy. One way to know whether an object will float or sink is to compare its density to the density of the fluid in which it is placed. An object floats if its density is less than that of the fluid. So an object floats if its density is less than that of the fluid. It will sink if the density is more than the fluid. Remember that density is the mass per unit volume. The density of the steel block is greater than the density of water, so it sinks. The wood block's density is less than that of water, so it floats. Suppose you formed the steel block in the shape of the hull of a ship filled with air, as in figure 14. So figure 14 up here. We have a ship. You have the hull of the ship. And then you have all this airspace in here. Okay? So it's taking up a huge area, a huge volume, but a large part of that volume is actually air. So in this case, you can actually get the buoyant force equal to the weight of the ship because you're displacing a lot more water because you have a lot more volume here. So now the same mass takes up a larger volume. The overall density of the steel boat and the air is less than the density of water. So the boat will now float. Remember, this is the steel boat plus the air. Now, Pascal's principle and pressure. So Blaise Pascal, 1623 to 1662, was a French scientist, and he discovered that pressure applied to a fluid is transmitted throughout the fluid. This is why when you squeeze one end of a tube of toothpaste, toothpaste emerges from the other end. The pressure has been transmitted through the toothpaste. In order to understand Pascal's principle, you must first understand pressure. So pressure right now, pressure from the air is pushing on you from all sides, like the pressure you feel underwater in a swimming pool. It's about 14 pounds per square inch, is what typical air pressure is. Pressure is force exerted per unit area. So our equation for pressure, we have pressure in pascals is equal to force in newtons divided by the area in square meters. Or we could say pressure is equal to force times area. Now, the SI unit for pressure is the Pascal, capital P, lowercase a. Because pressure is the amount of force divided by area, 1 Pascal is 1 Newton per square meter, or newtons per square meter. So really, you'd say 1 Pascal is equal to 1. So if you need to convert the units, this is a conversion you could use. Most pressures are given in kilopascals because 1 Pascal is a very small amount of pressure. We'll do example problems later. So Pascal's principle. The idea that pressure is transferred through a fluid can be written as an equation where pressure in equals pressure out. Since pressure is force over area, Pascal's principle can be written another way. So since pressure is force divided by area, we can basically replace pressure 1 and pressure 2 with, or pressure in and pressure out. So we can replace those with the equation for that. So you have input force divided by input area. That is our pressure in. The pressure out is output force divided by output area. Okay, so that's our equation for Pascal's principle. Now, hydraulic lifts. Auto shops or auto repair shops often make use of hydraulic lifts, which remove heavy loads in accordance with Pascal's principle. A pipe that is filled with fluid connects small and large cylinders as shown in figure 15, which is over here. Pressure applied to the small cylinder is transferred through the fluid to the large cylinder. With a hydraulic lift, you can use your weight to lift something much heavier than you. So you have your force applied here that basically causes this fluid to go into this chamber, and then you get a force out here. So, all right, Bernoulli's principle. So Daniel Bernoulli, from 1700 to 1782, was a Swiss scientist who studied the properties of moving fluids, such as water and air. Bernoulli found that fluid velocity increases when the flow of fluid is restricted. Placing your thumb over a running garden hose, as shown in Figure 16, demonstrates this effect. When the opening of the hose is decreased in size, the water flows out more quickly. Bernoulli examined the relationship between fluid flow and pressure. And you might think that increasing the velocity of a fluid's flow would increase its pressure, but Bernoulli found the opposite to be true. According to Bernoulli's principle, as the velocity of a fluid increases, the pressure exerted by that fluid decreases. He published this discovery in 1738. One application of Bernoulli's principle is the hose end sprayer. The sprayer is used to apply fertilizers and pesticides to yards and gardens. To use this sprayer, you have a concentrated solution of the chemical that is being applied, and that is placed in the sprayer. The sprayer is attached to a garden hose, as shown in Figure 17, which is down here, Figure 17. And a straw-like tube is attached to the lid of the unit. The end of the tube is submerged into the concentrated chemical, and the water to the garden hose is turned to a high flow rate. When you're ready to apply the chemicals to the lawn or plant area, you must push a trigger on the sprayer attachment, and this allows the water in the hose to flow at a high rate of speed, creating a low pressure area above the straw-like tube. The concentrated chemical solution is sucked up through the straw and into the stream of water. This concentrated solution mixes with water, reducing the concentration to the appropriate level and creating a spray that's easy to apply. So if we look at the diagram and kind of go through this, you have your container down here, you have your chemical down here, you have your straw-like tube coming up here. And basically what happens is as the water flow goes over top of this straw here, the pressure is decreased and basically will suck up the chemical, mix it with the water, and then it sprays out here. So, all right, viscosity. Another property exhibited by a fluid is its tendency to flow. While all fluids flow, they vary in the rates at which they flow. So viscosity is the resistance of a fluid to flowing. For example, when you take syrup out of the refrigerator and pour it, as shown in Figure 18, the flow of syrup is slow. Keep in mind this came out of the refrigerator, so it's cold. But if the syrup were heated, it would flow much faster. So if you heat it, it's going to flow much faster. Water flows easily because it has low viscosity. Cold syrup flows slowly because it has high viscosity. What causes viscosity? When a container of liquid is tilted to allow flow to begin, the flowing portion of the liquid transfers energy to the portion of the liquid that is stationary. In effect, the flowing portion of the liquid is pulling the stationary portion of the liquid, causing it to flow too. If the flowing portion of the liquid does not effectively pull the other portions of the liquid into motion, then the liquid has a high viscosity, which is a high resistance to flow. If the flowing portion of the liquid pulls the other portions of the liquid into motion easily, then the liquid has a low viscosity or a low resistance to flow. That takes us to the review questions.